Hey everyone, I just wanted to go over this progress check review with you guys since we didn't have a video on Thursday that was posted. I wanted to create one for you that has the progress check answers kind of worked out and explained. So you can feel free to fast forward to the part where you need help and get some extra help with that. So the first question is dealing with discontinuities and different types of. You have a piecewise function, you have a rational function. So in this rational function, we have a vertical asymptote. So here's my vertical asymptote. It is at x equals 3, and here's a little mini graph of that, and horizontal asymptote at 0. So my discontinuity is an infinite discontinuity. Okay, it is approaching infinity as you come from the right, and it's approaching negative infinity as you go from the left. And it is both infinity, so it's infinite. Okay, the next one is a piecewise function. You have two separate pieces here. You can go ahead and evaluate the function, do your little t-chart table, and get all the values to the left of 1 and then all the values to the right of 1. That's what these mean. This is all the values from like to the left of 1, and this is all the values to the right of 1. So I can say the limit of the function is x approaches 1 from the left. This is the left-hand side. When I plug in 1 here into my function, I'm going to get 1 minus 4, which is negative 3, but I'm going to take the absolute value of that, which is 3. So if I'm coming from the left, it's at 3. And then I'm going to come from the right. I'm going to plug in 1 again into this function. So 1 squared plus 2 is also 3. So if the limit from the left is the same as the limit from the right, but notice that neither one of these are equal to 1. So that means there's a hole right at 1. So at 1, 3, there is a hole because you're coming in from the right-hand side, and then you're coming in from the left-hand side, but then at 1, there is no particular value, but it's 3 on either side. Okay, so when you have the limit as x approaches negative 1 from the right being 3, and then the limit of from x approaches negative 1 from the left being 5, if you're coming in at the same x value and you have two different y values, that means it has jumped. The graph has jumped from one to the other. Okay, so that's why it is jumped discontinuity. And this last one says limit of the function as x approaches negative 1. That means as x approaches negative 1 from the left, so I'll write it down here, limit of the function as x approaches negative 1 from the right equals 7, and then the limit of the function as x approaches negative 1 from the left is also 7. When you say the limit of the function as x approaches negative 1 without a left or right hand limit, that means that from the either side, both sides, it is the same value of 7. So again, if it is the same value from both sides, and you have the actual value at negative 1 not being the same exact value, it's not a jump here, it's a point because it's coming in like this from the same side, but then at negative 1, there's a dot at negative 1, 5. Okay. All right, now sketch the function and evaluate the given limits. All right, so I started this off, and again, if you recall, we were sketching a function by starting at the restriction. So this is the values from 1 and less than 1. So I'm going to go 1, 0, negative 1. So when I plug those values in, 1 squared minus 1 is 0, 0 squared minus 1 is negative 1, and then negative 1 squared minus 1 is back to 0. Okay, so same color. I'm going to plot those values. And I know it's a quadratic, it's a parabola that's moved down 1. And so here's the shape of my left-hand side of this graph. All right, now the right-hand side, again, we're having an open circle here because 1 is not included. I'm going to plug 1 into this equation. 1 plus 3 is 4. Square root of 4 is 2. Minus 1 is 1. So at 1, it is 1. But there's a hole there. There's an undefined value. All right, I could pick more values, but I want to pick one that I can take the square root of. If I try 2, that's going to give me 5. If I try 3, it's going to give me 6. I want the value that's going to give me the next possible square root. And so this one was 4. The next one is going to be 9. So the value of x I want to use is 6. So when I put 6 in, I'm going to get the square root of 6 plus 3, which is 9. And that means the square root of 9 is 3. So 3 minus 1 is 2. So at 6, my value is 2. And there you go. If I go any further, it's going to go off the graph, off the grid here. So that's good enough. Okay. All right, so there is my square root function, and we're going to answer these questions now. As you go to the left, the limit of the function is going up, so it's infinity or it does not exist. As you go to the right, it is going to keep going up again to the right, so it's also infinity, does not exist. All right, now we want to do the limit of the function as x approaches -1 from the left. Well, I think I had meant that to be actually +1 because that's where you have a discontinuity. But if you're doing -1, according to what is being asked here, from the left-hand side, it's going to approach 0. From the right-hand side, it is also going to approach 0. So that means the limit of the function as x approaches -1 is 0. As long as they are the same, the limit is that value. Okay, so I'm going to go ahead over here and do the limit of the function as x approaches 1 from the right, and the limit of the function as x approaches 1 from the left. Okay, so from the right-hand side, as x approaches 1, we're going to be at this value right here. So that is 1. All right, now you're going to come to 1 from the left-hand side. So we're coming in from the left and approaching 1, and that is 0. So can I say the limit of the function as x approaches 1 is something? No, because from the right-hand side is a different value than from the left-hand side. There's a jump here. And that's why, like in this particular example, you had 2 different limits. That's when you get a jump. When you have the same limit and an undefined and a different value here, that's when you get a point or removable. Okay, so here, this one is does not exist. And it's regular does not exist. This one doesn't exist infinity. Okay, because it is just does not exist. The limit from the left does not equal the limit from the right, so that limit does not exist. All right, so we're going to evaluate the functions at f of -1. You'd use this function because the 1 is included there. We already have that answer, and that is 0. That's right there. F of 2 is over here somewhere, and again, you probably get a decimal value. I did not figure that out, so whatever that is, it's the square root of 5 minus 1, whatever that answer is. Okay, as a decimal. And f of 0 is right here, and that is -1. All right, so we had just said the discontinuity that exists is a jump discontinuity at 1. And then bounded, if you remember what bounded means that the function has either a minimum value or approaching a minimum value, or maximum value, or approaching a maximum value. So here we are going to say that it has a lowest value because the graph keeps going towards infinity this way and towards infinity this way. So that means it has an absolute minimum right there at -1. Okay, so it has a minimum. It's going to be bounded below. Okay, bounded above would mean it has a maximum. Okay, and then if it was bounded, it has a minimum and a maximum. So it has both a highest value as well as a lowest value. Okay, now one-to-one functions. One-to-one functions are functions that pass the horizontal line test. And we say for every x, there's a y. That's for any function. But for every y, there's also only one x. And that's when we have a one-to-one function. Each x and y are exclusive pairs. Okay, so we use the horizontal line test to kind of check for that. All right. And then over here, when you can see this one's one-to-one, this one's not one-to-one because it doesn't pass the horizontal line test. All right, then we have a couple of power functions here. And if you remember, if it's a negative power function, then it's going to be have a first quadrant that looks like this. And you're going to have to kind of decide if there's another piece to it or not. So this is x to the -3. And then when you do x to the -3, that is an odd exponent. So it's an odd function. So it's going to be symmetric over the origin or rotationally symmetric. And you can see this is going to be a one-to-one function. So yes, it's one-to-one. This one is even over odd. So if you remember the rule for even over odd, that was the one that is an even function. So it's also nice to know that any even function, I just like to think of a parabola, any even function kind of follow that same end behavior as a parabola. So when you know a function is even, you know it is not going to pass the horizontal line test. Any even function is not going to pass the horizontal line test. Now, whereas this one is odd over even. So if you remember that odd over even was a neither. It was not, even though it has an even number in the denominator, again, think of x to the 1/2 as your square root function. So it's going to look like this. So it is 1 to 1, so that is true, but it has no symmetry. Okay, so this is a neither odd nor even, but I'm not asking you for odd or even, I'm asking you for 1 to 1. So yes, it is 1 to 1. All right, modifying the domains to ensure that they're 1 to 1. Again, remember, if you have anything that's an even function, it's not going to be 1 to 1. So notice you have an x squared here. That means it's a parabola. This is a parabola that has moved down 16. And I actually drew this incorrectly because it is negative x squared. So it should be going the other direction. So it's going to be at negative 16 still, but it's going to go the other way. So here's negative 16. It's going to come around like this and look like that. But again, you were still taking this function and modifying it, so only the part, so it would have to be a function. So you're only going to take half of the parabola. So I'm going to take this and look at just the half, and we always use the right-hand side. So this is still the correct answer. So it's 0 to infinity. I'm not going to look at the left-hand side anymore. Okay, so then this one is an absolute value function that has moved right 3 and up 4. So here's the graph of that. And then my vertex of that is going to be 3, 4. Again, you can kind of just look at where it cuts down the vertex. The x coordinate of the vertex is going to be where you kind of cut that down. So that's at 3. So from 3 to infinity is going to be your restriction on that one. Same thing with this. This is move left 7 and down 1. So my restriction is going to be from negative 7 to infinity. So again, my vertex here is negative 7, negative 1. That negative 1 doesn't really matter. So you're just going to be using this x coordinate because you're looking at the x values. You're modifying the domain. So you're only looking at the x value. Okay, so here's where you're going to do f of g of x. Remember, this is the same thing. F, this fog and golf word is just the same as this. It means f of g of x. Okay, and this one means g of f of x. So you're going to find both of them for each of these functions, and you're going to identify and restrictions on the domain. All right, so if I'm doing this one, f of g of x, if you remember, if the inside function has a restriction, you have to worry about the inside function as well as your final answer. Since this is a linear function, it has no restrictions, and I'm putting it into this one first. So I'm going to do f of g of x. I'm going to get 1 over and plug in the 2x minus 3. So I get 1 over 2x minus 4. Again, your restriction is you don't want any denominator value to equal 0, so x cannot equal 2. So when you set this equal to 0, you get x equals 2. So that is the value that it cannot exist. It cannot be because it'll make the function not exist at that value. All right, so this one, I'm going to plug in f of x into this function. Now remember, the original function f of x is going in, so this has to be defined to be able to put into this. So the only value you can't use in this is 1. So let's see how that affects it when I put it in here. And I'm just going to simplify it a little bit. So that's a 2 over x minus 1, and then minus 3. So I'm in that rational function transformation form. Okay, so again, my only denominator is this minus 1. So x cannot equal 1 is still the restriction on my final answer. Okay, so if I do f of g of x on this one, this is a little bit longer. So let me use this color over here. Let's do f of g of x. So I'm going to have put in the x, this whole function g of x into this x. So I have the 4th root of 2x minus 6 minus 1. And then I have this plus 1 after that. And then take that to the 4th power, so 4th root. And then I have this plus 6 at the end. And I'm going to divide that by 2. Okay, so the negative 1, positive 1 cancels. So I'm going to get the 4th root of 2x minus 6 to the 4th, and then plus 6 over 2, which equals 2x minus 6 plus 6 over 2. Now I cancel those 6's out, and I get 2x over 2, which equals x. All right, these are this one's kind of long. So if I go the other way, I'm going to take this whole thing and put it in here. So I'm going to have a big 4th root here of 2 times the 4th root. I'm putting f of x into g of x. So the fourth root of 2 times this whole thing. So it's going to be x plus 1 to the fourth plus 6 over 2. So that whole thing times 2. And then I'm going to have a minus 6 after that and a minus 1 after that. Okay, so the minus 6 is in the radical, and then the minus 1 is outside of the radical. All right, so this is going to cancel like this. The 2's will cancel first, and then I'm going to get x plus 1 to the fourth plus 6 minus 6. And then minus 1 at the end. All right, now those cancel, and then I have the fourth root of x plus 1 to the fourth, and then I have this minus 1. And then you can see that the fourth roots cancel, so I get x plus 1 minus 1, which equals x. All right, are any of the functions in number 5 inverse functions? And how do you know? Yes, the way you can check something is inverse function is if f of g of x equals g of f of x, and they both equal x, then they are inverse functions. So number 5b, both equal x when I take one function and put it into the other, and then go vice versa. So they are inverse functions. And that is a check for two functions to be inverse of each other. F of g of x equals g of f of x equals, they both equal x. Okay? All right. This is verifying algebraically, and technically you guys really should be able to verify algebraically. In terms of your progress check, everything is multiple choice. If you know that something is even and you know that the whole function is going to be even if each of the pieces are even. So if I'm looking at this first function, cosine is an even function. That means when I put in a negative x, it is going to be the same as if I put in a positive x. If I put in a negative x for a square root, though, however, that is undefined. So that is neither even or not. So I have an even plus a neither. I'm going to get a neither. All right, now this one is odd over odd. So if you remember, odd over odd is odd. Odd over odd is going to be an odd function. So this one's odd. And then if I put in a negative x here, I'm going to get a sign, a negative sign x. That is the rotational symmetry, or symmetric over the origin. Okay, so here that is also odd. So they're both odd, so my final answer is odd. Here, absolute value, a regular function, is even. And then I have even over odd, which is also even. That is the option to give you an even power function. So even plus even is just going to be an even. All right, when you have a constant that is actually even, and then this was going to be an even exponent, so that's also even. So again, you're dealing with all even functions. My answer is even. All right, here's another exponent with a power function. So this one's even over odd. Even over odd means even. Okay, and then this is 4 over x to the third. So that one is odd, and this one is odd. So that's odd and odd. That means my final answer is odd. All right, so if I put these in order from least to greatest, you are looking at the exponent. So if I'm looking at something that is not in exponential form and I have a radical, I can always convert that. The square root of x to the third is x to the 3 over 2. Remember, you take this number over this number. Okay, and then I have another radical over here. I have square cube root of x squared. So that's 2 over 3. But since it's in the denominator, if I want to bring it up, it's going to be negative 2/3. So if I put these exponents in order from least to greatest, this is the smallest, h of x, and then comes f of x, that's 1.5, and k of x, which is, divide that, you're going to get 2.2, and then g of x gives you 3.3 when you divide that. You're going to ignore the coefficients. It's going to be irrelevant as x grows to towards infinity. It's going to be the exponent that kind of takes over. Okay, so always watch the exponent on here. And I said, determine the symmetry for each of these as well. All right, so here I got odd over even. Odd over even is the one that is just first quadrant. So this one is neither. Okay, neither odd, even, nor even. This one is even over odd, and that is the one that is even. Even over odd is even. So this one is over the y-axis. Okay, so or even or symmetric over the y-axis. This one is even over odd also, but it's negative. It doesn't matter. We're still looking at the numbers, even over odd. So that is also even. And then this one is odd over odd, which means the final answer is odd. Okay, and then here's your answers for each of these graphs. Again, this is even over odd. That means it's going to be symmetric over the y-axis. Remember, we drew just the first quadrant, and then based on the symmetry, we finished the rest of the graph. So even over odd means it is going to be an even function. That means it is symmetric over the y-axis. Okay, so then this f of x is this one right here, and it's going to be below the line y equals x because the exponent is less than 1. So I'm going to draw a first quadrant, and I'm going to make it symmetric over the y-axis. Right, this is odd over even. That means it is going to be the one with just the first quadrant. It is more than 1, so it is above the line y equals x. And then I'm not going to draw anything else on the other sides because that is it. Okay, so this one's neither. This one is odd over odd, and that is greater than 1. So it is going to be above the line y equals x in the first quadrant. And then we're going to make it symmetric over the origin, or rotationally symmetric, and it's going to be going into the third quadrant over here. All right, which of the three functions approaches its end behavior the fastest? Well, the biggest one is h of x, is the biggest exponent, so that is going to go the fastest towards infinity. All right, so rational functions, again, make sure everything is factored if you can. Factor it first. Then you want to look at vertical asymptotes and horizontal asymptotes and so on, and figure out all these characteristics. Okay, so if I factor this, nothing cancels out. And then I notice that it is top heavy. So it is top heavy, meaning that it is going to have not a horizontal asymptote, but an oblique asymptote. So you got to do this division to figure out the oblique asymptote. Again, you're asking yourself, how many times does x go into x squared? In other words, what are you multiplying x by to get to x squared? And that's an x. So multiply that by x, I get x squared. I get multiply that by 3, and I get plus 3x. And I write that down and subtract. I'm going to get a negative 5 when I subtract that. So negative 5x. Bring down the plus 1. What are you multiplying x by to get negative 5x? It's negative 5. So I'm going to write the negative 5 up here. And again, multiply that negative 5 times x and the negative 5 times 3. So I get negative 5x minus 15. Now this last part is going to be the remainder, and it's not going to matter in terms of your equation. This is your answer in terms of your equation. You're going to set y equal to that. Y equals x minus 5. Okay, vertical asymptote comes from the denominator equaling 0. So x plus 3 equals 0. It means x equals negative 3. The zeros are where the numerator equals 0. So I'm going to do x minus 1 equals 0 and solve for that. I get x minus 1 equals 0, and I get x equals 1. And that's why it is 1, 0. The y-intercept is found by putting 0 in for all the x's. I'm left with 1 over 3. So I have the coordinate as 1 over 3. All right, the limit of the function as x approaches negative infinity, and limit of the function as x approaches positive infinity. So I'm going to go ahead and put this in my calculator. I mean, I could draw it as well and get a bunch of points, but that would take a lot longer. So I'm going to put the function in the calculator, y equals, and that is x squared minus 2x plus 1. I'm going to put that in parentheses. I'm going to put it in the calculator and divide it by another parentheses around the x plus 3. Okay, and then when I go to graph that, I can see that as I go to the right, the graph is going to go along that asymptote. Actually, that it's a slant asymptote, so it's going to go to infinity. It's going to go up along the line y equals x minus 5. All right, and as I go to the left, when I look at the function, it goes so you have to actually look at the function to the left-hand side because I'm looking at the points, because on your actual calculator on the graph, if you just look at the screen of the window, it doesn't show enough. It's going to look like it's going to infinity. It is actually going to negative infinity. So make sure you go to your table and check the values. All right, so if we do this one, you factor it, and you can see that the x plus 3's cancel out. It is the same degree on the top and the bottom, so it is going to have a horizontal asymptote, not an oblique asymptote. So my horizontal asymptote is y equals, and since it's the same degree, I'm going to take the coefficient. So it's 4 in the numerator and 1 in the denominator. So y equals 4. That is my horizontal asymptote. My vertical asymptote, I'm looking at the simplified version here, and that's x equals 3. My zeros are where the numerator equals 0. So the only thing I have in the numerator is a 4x. So 4x equals 0. That means x equals 0. So my coordinate is 0, 0. My y-intercept is where y is 0. So I'm going to get 0 over negative 3, which is just 0. So again, it's the same as the x-intercept because that has the same coordinate 0, 0. All right, the limit of the function as x approaches negative infinity. I think I did this one backwards. The left was negative infinity and the right was infinity. I didn't look at that carefully. All right, so as I look at the function as x approaches negative infinity for this one, I put it in my calculator. I have 4x squared plus 12x parentheses divided by parentheses again, x squared minus 9, parentheses, if I go to my graph. Okay, it is a little difficult to see. So it looks like it's approaching this asymptote. Since I have a horizontal asymptote, my left and right end behaviors is going to be approaching that asymptote. Even if it crosses it at some point, it should still go back and get closer and closer to my horizontal asymptote. So that's the one thing nice about having a horizontal asymptote. You're going to get both of these values approach that horizontal asymptote. And then do we have a hole here? Yes, because we have something cancel. So we're going to set x plus 3 equals 0. And then we saw that we get x equals negative 3. Now to actually find the coordinate of the hole, I'm going to put negative 3 into my simplified version here. So I have 4 times negative 3 over negative 3 minus 3. So that's negative 12 over negative 6, which simplifies to a positive 2. So my coordinate of my hole is negative 3, positive 2. Okay, last page on my review. All right, vertical asymptotes is where the denominator equals 0. So I went kind of quickly here. We got x equals negative 5, we got x equals 3, and we got x equals negative 4. We did have something cancel, so we have to know that that's going to make our cell, the graph have a hole in it. Okay, so again, I have a horizontal asymptote. I'm not even going to bother looking at my graph this time. I didn't think about that in the last example, but it's going to be approaching that asymptote on either side. So it's going to be 0 here and 0 here. It is bottom heavy. That's why I know automatically my horizontal asymptote is y equals 0. Your y-intercept is where x equals 0. So this is in factored form. You're actually going to have to put those zeros in. So I have 0 plus 3 is 3, and then 0 plus 1 is 1 over 0 minus 3 is negative 3, and then 0 plus 5 is 5, and then 0 minus 4 is negative 4. All right, so we're going to get, that's going to cancel with that, but leave a negative 1. And so that's going to be 1 over a positive 20. So my coordinate is 0, my y-intercept, right? 0, 1 over 20. All right, my hole, I'm going to do the same thing. I'm plugging 2 into my simplified version. So I have 2, and then I have my coordinate would be 2 plus 3 is 5. And then 2 plus 1 is 3 over 2 minus 3 is negative 1. And then 2 plus 5 is 7. And then 2 minus 4 is negative 2. All right, so I'm going to get 15 over 14. So this is going to be 2 15/14. Okay. All right, last question. Nothing actually cancels here, even though they factor. So nothing's actually going to cancel out here. All right, so my vertical asymptote is my values that make the denominator equal to 0. So I have 2 of those. It is top heavy, so I'm going to have a slant asymptote. I am not going to have a hole because nothing cancels. My zeros are where my x values are equal to 0. So if I factor this further, I can see that's going to be x minus 1 and x plus 1. And x plus 2 in the numerator over x plus 4 and x minus 3 in the denominator. So that's going to be my zeros are going to be 1, 0. It's going to be -1, 0, and -2, 0. Okay, so you're going to have 3 x-intercepts. Remember, zeros are your x-intercepts. Your y-intercept is where x is equal to 0. So I'm going to put my zeros in here. So I have 0 minus 1 is -1. So I'm putting it into this one. So 0 squared is still 0. So 0 minus 1 is -1. And then 0 plus 2 is 2. I could also put it into my original. And then 0 plus 4 is 4. And then 0 minus 3 is -3. All right, so I get -2 over -12, which simplifies to 1 over 6. So my answer is 0, 1, 6. Okay, and then to figure out your slant asymptote, you got to do this division. And it looks really long. X squared plus x minus 12 goes into this whole thing. X cubed plus 2x squared plus 2x, yeah, x squared minus x minus 2. All right, when you do the division, again, you're just looking at your lead terms and you're trying to figure out how many times does x go into, x squared go into x cubed, or what are you multiplying x squared by to get x cubed? And that's just x. So when I multiply this, I'm going to get x to the third, and x times x is x squared, and x times -12 is -12x. And now I'm going to subtract. So subtracting this whole entire thing means I'm going to make sure I watch the signs there. That's going to disappear. And then I get 2x squared minus x squared is just going to give me x squared. And then -x minus -12 is going to give me positive 11x. Okay, now you're going to ask yourself, does x squared go into x squared? Yes, you multiply that by 1, so plus 1. All right, this is going to cancel this after this. So 1 times x squared is going to be x squared. And then 1 times that is plus x, and then minus 12. And when you subtract, that goes away. And then this is going to be 10x and plus 12. And x squared just no longer goes into that number, so that is your remainder. So my answer for my slant asymptote is this: y equals x plus. Okay? All right, so that was the review, and that is it.